Alright everybody, so today I thought I'd make a video that's a summary of what critical numbers are and how to think about the first derivative test. In this video, by the time you would watch this video, you already know what a critical number is and you've already seen the first derivative test. So you've got some familiarity with both of these things. But like it says, this is just a summary. The examples I use in this video are not very intricate and don't involve very complicated math. The examples I'll show you in this video are fairly easy. I just, as this is a summary, wanted to get a lot of information in one place. Okay? So the math's not complicated. It's mainly about the ideas. So this video might be something that you'll look at if, based on the other videos, you felt like you could do the math and you felt like you understood the steps as I went through the problems, but you're still a little vague on what a critical number is and why it's involved in the problem, or why to use the first derivative test and what that tells you. Okay? So let's get to it. So what's a critical number? If we're going to make a summary video or any video about critical numbers, we should start by making sure everybody knows what it is. So a critical number, if you have a function or curve, call it f of x, then some number c, let's just say c for now, I'm using a variable there, some number c is a critical number if the derivative is either 0 or undefined at c. Okay? And you'll see examples of both of those in the video. So that's just what a critical number is. We can't argue with that because it's a definition. Okay? Now, as far as like, well, what does if the derivative was 0, what would that mean? And why do we bother to find out? And if the derivative was undefined, well, what does that mean? And why is that also a critical number? Well, those are both things that we'll address in the video. Okay? As we go through it, little by little. So first, so why do we care? Or why would somebody care? I mean, I can't say that everybody who takes calculus cares what a critical number is, but as far as the broader picture of math goes, why would we care about critical numbers? Well, we use them to find out, ultimately, whether there's a local maximum or minimum point on a curve. Okay? So it turns out that if a curve has a local max or min at the point x is equal to c, then x is equal to c must be a critical number. That number c has got to be a critical number. So think of it, it's if and then. If there's a local max or min on a curve, then there has to be a critical number at that point. All right? However, some fine print, I guess you could say to that, is if I reverse that statement, such as if c, that number c, is a critical number, then it may be the case that f of x has a max or min or doesn't. Okay? So if there is a local max or min, there must be a critical number at that spot. But to turn it around, if you have a critical number, it doesn't mean that there's a max or min at that spot. Alright, so I guess this is the one that's maybe a little harder to understand, but it just means if we're doing our math and we find a critical number, we have to check to make sure somehow that that point is actually a maximum or min. Okay? Alright, because it may or may not. Just because a number is a critical number doesn't mean that there's a max or min there. Now, if you're just good at taking in ideas, like somebody can just tell you something and you understand it, then that's wonderful. Most people, at least most people that I come across, need to see examples to really start understanding the ideas. So I'm going to show you lots of examples in this video. And hopefully through the examples you can kind of put together in your own mind how the ideas work. So let's take this curve right here. 2x third plus 3x squared minus 12x plus 1. Now I said I wasn't going to get into the details, the very fine details about the math in this video, and I'm not, but doing some of the math is essential. Alright, so here's the curve. Alright, here's the derivative. 6x squared plus 6x minus 12. So this derivative could be 0. That's a possibility. But it's never going to be undefined. I mean, 6 times a number squared plus 6 times a number minus 12, that's always going to have an answer. It's never going to be undefined. Things are undefined, such as division by 0 or roots of negative numbers. Those sorts of expressions we might say are undefined. Okay. So say I get the derivative and I work on it a little bit and I factor it into this. Well, what that would tell me is 1 and negative 2 are critical numbers. Now, let's see what that means about the graph. If you were to draw the graph, and here I've just sketched it just so that you could see what these critical numbers corresponded to on the graph, then at x is equal to negative 2, it turns out there's a local maximum. And at x is equal to 1, it turns out there's a local minimum. Okay? So, all right, the derivative is 0 at 1 and negative 2. It turns out to mean that not only do we have a max and a min at those points, but it's because the curve is flat there. The curve rises, turns around and falls and turns around and rises. Okay? All right. So there's one example of these critical numbers and how they look on the curve. All right, let's look at another one that turns out to be very different. So what about this curve here? And I'll say curve in quotes. It's not really a curve. It's not bent or curve, or it doesn't turn or anything like that. So f of x equals absolute value x minus 3 plus 4. So there's no formula for finding the derivative this time. Okay? On this last example I showed you, there's a definite procedure. There are rules and formulas, whatever you want to call them, for finding f prime. With this example, that's not true. All right, the way that I would find f prime, I guess there's a few ways you could do it, but I think in another video I mentioned that this could be done by looking at the curve. So if this is the curve, y is equal to f of x. And I noticed that it's 2 straight lines that meet at a common point. And the slope of this line up until you get to 3 is negative 1. Okay, so the derivative is negative 1 if x is less than 3. Slope's negative 1, slope's negative 1, slope's negative 1 everywhere on this curve up until you get to 3. And then the slope is 1 at all points bigger than 3. So since the derivative, one interpretation of it is that it tells you the slope of the curve, that means that the derivative would have to be negative 1 if x is less than 3 and 1 if x is greater than 3. Now, what about at that point down there, which is a corner point? What are we going to say about the derivative? Well, if this is the derivative, it's never going to be 0. Okay, it's either 1 or negative 1. But implied in my less than and greater than is that it's undefined at 3. There's no way to measure the slope at the corner. Here's a line of slope negative 1, and here's a line of slope 1, but where they meet, the slope isn't anything. So the slope is undefined at a corner point. Now we would say that, well, this curve has a critical number of 3. Because it's, as a matter of fact, true that the derivative is undefined at 3. All right? Now, it also turns out that by the shape of the graph, 3 is a local minimum. Okay, you can see it right there. The curve falls down to that point where x is 3 and it rises on the other side. You look at it and you can tell it's a local minimum. So we have a curve, a critical number found through the derivative being undefined. Okay? And it turns out that at that point, where the critical number is 3, there happens to be a local minimum. Okay, now, so there you've seen some examples of cases where the critical number turns out to be a local maximum or minimum on the curve. But what about these examples where if you had a critical number at, say, a certain place, then there may or may not be a max or min. Okay, so what about the examples where it's not a local max or min at the critical number? Let's see what those look like, just so you can see that it could go either way. All right, so here's another curve where, again, I'm not going to delve too deeply in the math. I really just wanted you to see a bunch of examples in this video. But say we take this curve right here, and we find the derivative, and we say, well, that derivative, that's never going to be undefined, but it could be 0. So I factor it and I work on it a little bit, and I say, okay, if f prime ultimately is 3 times x minus 4 squared, that will never be undefined, but it will be 0 if x is 4. Okay, so what's that mean? It means 4 is a critical number, because critical numbers are numbers that cause the derivative to be either undefined or 0. 4 makes the derivative 0. Okay, so it's a critical number. Now, what does that mean for the graph, though? Is there going to be a maximum there, a local maximum or a local minimum? One thing I was just telling you is that just because you have a critical number doesn't mean that there's going to be a local max or min there. There may or may not be a local max or min. Let's see how it works out this way. Here's the graph of that curve. So what it does is this curve rises very gradually up until 4, up until you get to x is equal to 4, where it flattens out. It becomes horizontal. Like right there at 4, the derivative is 0. That means the curve is horizontal. So it rises and it tapers off and flattens out, and then it continues rising. Okay? Well, would a curve like that have a local maximum or minimum? Well, no, it doesn't have the right shape. In order to have a minimum, you have to fall and then rise, and in order to have a maximum, you'd have to rise and then fall. So this doesn't do either of those things. It does not have the right shape to have a local max or min, even though we found a critical number. So just because a curve has a critical number doesn't mean that there's a max or min at that point. Okay, here's an example of a curve that has a critical number at 4, but does not have a local maximum or minimum there. Okay, so let's see one more, and then I think we have a decent survey of basic examples, all right? So what about this one? F of x is equal to x plus 3 to the 1/3 power plus 4. All right, so say we find the derivative of that. Not too hard to do that with the rule. And then I rewrite it a little bit, and I notice it's a fraction. It's 1/3 times x plus 3 to the 2/3. Well, if that's your derivative, it will never be 0, because 1 divided by some other number is never going to be 0. That's the way arithmetic works. The only way that you can divide and get 0 is if you divide 0 by some other number. And if you got a 1 up there, it's just not going to happen, okay? So if that's your derivative, it will never be 0, but it could be undefined. In fact, it's undefined at -3, because that would cause a division by 0 in the derivative. Okay, so it's undefined there. What's that mean? Well, a critical number is defined to be a number that makes the derivative either 0 or undefined. So since -3 makes the derivative undefined, -3 is a critical number, okay? What's that mean for the graph? Does it mean that there's a maximum or minimum at that point? No, it doesn't mean either way. It could go, maybe there is, maybe there isn't. We'll just have to look and see, okay? So here I sketched the graph, and my disclaimer, I didn't mention on the other graphs that the shapes are correct on all the graphs. They're all hand-drawn, but the shapes are correct. They may not be to scale, though, okay? Because they don't need to be for me to show you what I need to show you. So there's my disclaimer. But anyway, so there's your curve, and what I notice about it is it rises, and it becomes extremely steep, so steep that it's vertical at the point x is equal to -3. And I guess another disclaimer is I say the curve's vertical at -3. It'd be more proper to say it had a vertical tangent line at x is equal to -3. But anyway, for our purposes now, we'll say it's vertical right there at 3, and then it falls off a little bit and continues to rise. Okay, so it's not very steep. It gets steeper and steeper and steeper. It's vertical. It gets less steep and flattens out a little bit, but it's rising the whole way through. Okay, so if that's the shape, is there a local max or min? This curve doesn't have the right shape for there to be a local max or min. This critical number, which came from the derivative being undefined, the reason why the derivative was undefined at -3 was because the curve was vertical. Do you see the logic there? Well, so what's the derivative tell you? Well, one thing it tells you is the slope of the curve. If the curve was vertical at -3, well, what's the slope of a vertical line? A vertical line, there's no way to measure the slope. We say a vertical line has an undefined slope. Sure enough, the derivative is undefined at -3. So that's the connection between the derivative being undefined at -3 and the curve, in fact, being vertical there. Now look at the shape. Does it have a maximum or minimum? No, it doesn't have the right shape to have a max or min. The curve does not have a local max or min, despite the fact that there's a critical number at -3. Okay, so what do we take away from this? You've seen some examples. Say, well, if there's a critical number, if you have a curve and you find the derivative and you find the critical number, if there is one, that doesn't mean there's a max or min. You'd have to check somehow. You'd have to have some idea what the shape was to know if the critical number was due to the fact that there was a maximum or minimum point. Okay? All right. Now we've seen some examples now. We've seen cases where the derivative was 0 or the derivative was undefined. Let's think about this. So say you find a critical number. How can you tell if the curve has a local max or min at that point? How do you know? You know, with this one, you know because I showed you what the graph looks like, because that's something I wanted you to see. But in most of the problems in the quizzes and the lessons and the tests and so on, they're going to be too complicated to draw, and we're going to have to see through the equations whether there's a local max or min. So how can we tell? If we find a critical number, how can we tell if there's a local max or min at the point? Answer is that we just use the first derivative test. Now, I won't state the first derivative test in the way that you would find it in a textbook, because I've already done that in another video. This video is just a summary, something I hope to be fairly quick to put all the information together. What the first derivative test tells you is the shape of the curve. It's a way of knowing the shape of the curve. So see this curve? It's falling, and then you'll have a critical number at that spot. The derivative will be 0 there at that point at the bottom, and then the curve's rising. It has the shape to have a local minimum because it's falling and rising. Okay? If you made a chart of the derivative versus x, you would find that the derivative is negative to indicate the curve is falling. And on the other side of the critical number, the derivative is positive to indicate it's rising. That table indicates this shape, and that shape indicates that there's a local minimum at the critical number. Okay? So the first derivative test is just a way of thinking about the shape without drawing the graph. You'll make a chart like this, and that gives you a way to imagine what the shape is and determine if there's a local minimum or maximum. Okay? Other possibility might be this, like say here this curve is rising and rising again. It's vertical right there. That's where the critical number would be, as we saw an example just a minute ago. If you made this table of the derivative versus the x-axis, you would find that the derivative is positive left of the critical number, meaning the curve is rising through that interval. Positive right of the critical number, indicating that the curve is rising on that interval also, and undefined at the critical number. In this case, indicating that the curve is vertical. Now, even if you couldn't see that, you'd say, well, it's rising, so it's going up, and then something happens at the critical number, but then it continues to rise. How could it have a local max or min? It has to fall and then rise, or rise and then fall to have a local max or min. What the first derivative test says is that the derivative has to change signs through the critical number. That if c was a critical number, that would have to be plus and minus, or minus and plus, for there to be a local max or min. So if you found a critical number and these signs on either side were the same, there won't be a max or min. You can think of it like that. You can think of it by imagining shapes if you wanted to. I hope that even if we don't understand the math so well, we can all look at that and say, yes, a curve that has this shape wouldn't have a max or min, okay? And I guess that would be the starting point to understand what the first derivative test is and what critical numbers have to do with it.